All right, we're about to dive into something that feels a lot like digital magic. It's a technology that lets computers do more than just read words. It lets them actually understand the relationships between them. And let me tell you, this one idea completely changed everything for artificial intelligence.
So, we're going to start with a concept that seriously sounds like it was pulled straight from a science fiction movie. But what you're about to see is a very real thing, a capability that really marked a turning point for AI. So, here's the big question. Can a computer really do math with abstract concepts? I mean, can it take an idea like royalty or a capital city and just plug it into an equation? It sounds kind of impossible, right? Well, let's take a look. Now, this right here isn't just a clever graphic. Nope. This is a real calculation. A computer can take the concept of king, subtract the concept of man, then add the concept of woman, and the closest idea it finds in its entire vocabulary is queen. This is, quite literally, the algebra of meaning. And just to show you it's not a one-off trick, it works for all kinds of relationships. For instance, if you take Paris, subtract its country, France, and then add another country, like Italy, the computer correctly figures out that the answer is Rome. I mean, that shows a deep conceptual understanding, not just memorization. So how on earth is any of this possible? Well, the secret is to stop thinking about words as just text. Instead, start thinking of them as locations, like coordinates on a giant, multi-dimensional map of meaning. And this gets us to the core technology that makes it all happen: word embeddings. The key idea here is that every single word gets translated into a long list of numbers, what we call a vector. These numbers act just like coordinates, plotting the word's exact location inside that huge map of meaning. You have to realize what a massive leap forward this was. The older methods, like something called bag of words, basically treated every word as a totally separate thing. They could count how many times a word appeared, sure, but they had no clue that king and queen were related. Embeddings, though, they're all about capturing those relationships, which is what lets us do that incredible word math we just saw. But wait, how does the computer even build this map of meaning from scratch? It's not like someone is feeding it a dictionary. It has to learn all these relationships entirely on its own. So, here's how it does it. The thinking behind it is surprisingly simple. A model just reads a staggering number of sentences. We're talking billions. And for any given word, it tries to guess which words are most likely to show up next to it. If it gets the prediction right, it thinks, okay, this word's coordinates are probably good. If it's wrong, it just slightly adjusts the coordinates and tries again. You do this billions of times, and eventually, words that show up in similar sentences end up with very similar coordinates. And this whole process really boils down to this classic idea in linguistics. It makes perfect sense, right? Words like dog, puppy, and poodle are almost always going to be surrounded by words like walk, fetch, and leash. Because they keep the same company, the model naturally learns to place them close together on its meaning map. Okay, so that's the theory. Now, let's actually look at the specific models that brought this idea to life. We'll even take a peek at how you can do this yourself with just a few lines of code. It's actually not that complicated. There are a few famous models that really put word embeddings on the map. Word2Vec from Google was a huge breakthrough. Then you had models like Glove from Stanford and FastText from Facebook AI Research, and they all built on those initial ideas with their own clever improvements. For example, Word2Vec looks at whole words at a time. FastText, on the other hand, breaks words down into smaller pieces, like chunks of characters. This gives it a really cool advantage. It can make pretty good guesses for words it's never seen before, and it's much, much better at handling things like typos or misspellings. So, let's make this a little more real. In a programming language like Python, there is a fantastic library called Gensim that makes playing with these models incredibly easy. To get started, all you have to do is import the Word2Vec model, just like you see here. This one line gives you all the tools you need to get going. Next, we just create our model. We'd start by feeding it a bunch of sentences. That's our training data. Then we just tell Word2Vec to go to work. We can also give it a couple of simple instructions. For example, vector size equals 50 is just as telling it, hey, make each word's coordinate 50 numbers long. And min count equals 1 tells it not to ignore any words, even if they only show up once. With that single command, the model starts building its map. And finally, we can test it out. This line of code is just asking our new model a simple question: what word is most similar to the word learning? Now, if our training data included phrases like machine learning is cool, the model would have learned that learning and machine often show up together. As a result, it would correctly tell us that they're closely related. So, after all that training on billions of sentences, what does this meaning map actually look like? Well, when we use some special visualization techniques to squish it down into 2D or 3D, something pretty incredible starts to emerge. We get a whole universe of words. And in this universe, words that are related just naturally drift toward each other. You'd find a dense little neighborhood of animals, dog, cat, fish, bird, all huddled together. Somewhere else, you'd find a cluster of colors, red, blue, green, and another one for food. It's visual proof that the model successfully learned all these relationships just by observing the company that words keep. And what's so important to get is that this is not just some clever party trick. Word embeddings are a fundamental building block for almost all modern language AI, from the autocomplete on your phone to the biggest search engines. In fact, these very concepts are the direct ancestors of the massive models like GPT that are completely changing our world today. So we've seen how computers can literally master the algebra of meaning, turning our messy human language into a vast navigable universe. It really makes you wonder, if we've already managed to map the entire world of words, what complex idea are we going to map next? And what are we going to discover when we do?